if you're doing your research process, you've got your data, you've collected this brilliant design, you've figured out what you have it in hand, you've made a beautiful picture, you're going to make a giant poster, put it on your wall, and someone's going to say, you're going to say, look at my centrality score is 15, and someone's going to say, is that big? You're going to go, I don't know, right? And so the plan today, right, is to put the kinds of measures, the descriptive measures we've talked about the last few days into context. And what we would normally do in a standard sort of modeling class is we'd say, well, I've observed two groups. I've got men and women. I ask how often they do dishes, and I take a sample, a random set. I see that men do dishes about, once a month when they have nothing else to wash on, and women do dishes every day, and I get difference in mean, and I see what the variance of that is, and I calculate a standard error, and I say that in fact they're statistically different in the population based on the sample that I have, right? And so I can say that difference is big. And we do that because we have some random sample of the population, and we're inferring to the population as a whole. In networks, the problem is a little hard, and this came up sort of hinted at yesterday, in that if I go in and I do a village survey, right, in a country somewhere, and I collect information from every person in the household, right, every household in the village, I might have 1,000 observations. I've done 1,000 interviews, but I have one network, right? And so because I have one network, what population am I trying to infer to? Right? And it turns out that substantively and statistically, we often have a slightly different understanding of what that inference is. Right? On the one hand, substantively, what we really want to know is that if we were to go into a bunch of different villages and do this again, right, or do our intervention again, or something like this, would the effect hold? Is there a causal association there in some real sense? And statistically, we can't know that because we didn't sample 100 villages or 1,000 villages or whatever we need to get the power to figure out if the cross-village differences, these things is different than zero, right? And so we need some other way to think about it. And what we're going to do today, it turns out that we're not completely in the dark. We don't have to throw up our hands and walk home. We have ways of doing this, and that's what the statistical modeling of network is all about. And to get there, we need to think about a slightly different sort of inference problem, and we're going to then go through ways in which we approximate the actual inference problem we have. There's an old trick in most of academics, which is that if you can't solve the problem that's been given you, sort of redefine the problem, and that's effectively what we're doing, right? So we're going to slightly redefine the problem about what inference is, and I think it's not a bad redefinition. I think it's actually, in the case that we're dealing with, quite useful. And we're going to do it across a couple of different steps. So the first thing we're going to do is we're going to talk about this inference idea. Then we're going to essentially come up with the notion of different types of randomization. And so the solution, it turns out, to the problem that we have is to think about our graphs as a subset of a universe of graphs that could be achieved out there, as opposed to our actual population that's in the world. And so what we're going to do is compare our observed network to this universe of possible networks that are out there. Now, generating that universe of possible networks turns out to be a bit of a pain in the ass, but we're going to figure out how to get there, at least an approximation. And then we want to think about it in two sorts of ways. On the one hand, if we're thinking about networks as independent variables, if we care about our networks because they're associated with some outcome, we want some way to compare the association, the correlation, or the regression coefficient, or something like that, to this set. And a very simple way to do that is known as QAP modeling. And so QAP is a non-parametric randomization approach to compare and observe to a randomized distribution. It's a very simple set, and statisticians are a little about it because it's a little overpowered, if you will. It's pretty easy to find an association. And so you should raise your bit, but I'll get into the details of that in a bit. And we have other ways of doing it, but it also introduces the idea that we're going to come to later, which is what David Schaefer is going to be giving us all tomorrow morning on a more statistically rigorous approach to doing that kind of causal inference for a network as an independent variable. In order to get to that set, though, we need to also think about networks as dependent variables, because the real threat to inference, it turns out, and this is what you get for the second half of the Moody show this morning, you get me all day. I mean, I'm literally here all day today. You guys are going to be so sick of me, it's not even funny. What's the line? We're going to be winning so much, you're going to be tired of winning. I think that's where we're going to be at today. But the thinking is that we need to think about ways of modeling networks, because when we actually come to the inference problem for health outcomes and other sorts of substantive things that we care about, we really want to think about how the network structure affects the behavior, and both things are changing simultaneously. So of course we then actually need two models. We need a model for how the network is changing and a model for how changes in the network affects the behavior, and that ends up becoming these two-stage models we call stochastic actor-oriented models, which is what Dave is doing. So really, my entire purpose in the next hour and a half or so is to set the stage for the work that you might want to do when Dave is here. All right. So we all on board for where we're going? Are we doing it? Any other logistical problems in my other sort of management hat that I should be worried about? All right, let's get this show on the road. In order to think about the inference problem, is that where I'm at? I thought I was expecting something else. Yeah, okay. We're going to think about a sequence of randomization problems. And what was introduced yesterday was this notion of an Erdos-Randi graph, Erdos-Randi random graph. Peter was talking about this, that if you just take in, as part of your expected value for the modularity score, if you were to take a network and flip a coin, you could get what's known as a random network, right? I can just take an adjacency matrix and flip a coin on each cell, and that would give me a random graph. And that ends up being the root of a whole series of more complex models for thinking about network randomization. And so we have the kind of configuration model where we have the expected degree distribution, that we talked about before. So if I know everybody's row sum, and I know everyone's column sum, I know the expected value is the intersection of those things, right? And so those models lead to a series of finer refinements about what we do to rows and columns, essentially, and ways in which we deal about patterns of rows and columns. And that gives the idea of this notion of a P-star model. On another sort of entire branch of this model, we were dealing with, well, you really can't see the resolution on that, can you? That's really true. That says arbitrary mixing models. And that moves us through to a series of things where we're actually trying to deal with connections between nodes based on some other behavior set, including network autocorrelation models, QAP models, and these Siena models. And so we're going to get to all of these pieces. It's so nice and clear on my screen. That's really too bad. You should see what I see. Take my word for it. So that's where we're going today. We're not going to talk about all of these models. I'm going to talk a little bit about random graph models. I have a pointer. I guess I can use that. Whoa, not like that. So we're going to talk a little bit about the random graph models, and then we're going to move through and spend most of our time today speaking about these ergom models and a little bit about some of the others. Okay? All right. So because we don't have a sample of a universe of networks, with the folks in the back, would somebody flag me down if I'm getting close to the time? Because otherwise I might just go on forever. So, and I'm going to be going on forever, but I need to shift gears about what I go on about. So we need to be sure that's there. So the idea that we want to think about then is what are we trying to infer to? And since we can't take an observed statistic and infer that to a population, if we're not doing a sampling inference, we instead want to ask if we're going to infer to this universe of random graphs that are or of graphs like the ones we've observed. What we tip to do is change the question a little bit. And what we say is the question is, would we see the observed graph if the process that generated this graph were random? Right? So instead of saying I have an unknown process out there and descriptively I want to know if A is different from B, what I want to know is that if the process that I'm interested in of how networks are formed, if the network generation process were essentially random, would I get the same result that I've observed? And what we're going to do is we're going to narrow down that question, because it turns out that the obvious answer to the first question is no, right? So if the world were random, it would be a disaster. Nothing would be good there. So of course it's not really random, but it might be conditionally random. It might be random given a series of things that you don't care about, right? And so once I control for those things that I don't care about, do I essentially recover the graph that I have, and everything that I'm interested in is just epiphenomenal on something like the neighborhoods that people live in or something like that. And so in order to get to this point, what we're going to do is we're going to take our common association tests like correlations, regression, and so forth, and we're going to sort of generate the assumption of case independence by doing it through simulation, right? So essentially what we have, instead of assuming that we have independent observations and that our correlations and such, so we're instead going to say, let's just let the world be random. Let's pretend. And this is one of the things that was impossible to do before the computational revolution in work. So we need to find a way to do this in a computationally efficient and effective way. And so the big picture story here is what we're going to do is we're going to ask this kind of question. So is the observed graph the one we would see if the process were random? Then we're going to go through a lot of work to figure out how to generate an appropriate random null model. And then given that appropriate random model, we're going to compare our observed to our randomized set. So that's the big picture algorithm. If you remember nothing else about how this day goes through, that's where we're going, and that's how it works. But there is this core difficulty, right? Which is that what you would like to do is compare your observed graph to the set of random graphs that are like your observed graph. And that's a really loaded phrase. So what is the set of random graphs that are like your observed graphs? It's the universe of all possible graphs with the same number of nodes and edges, for example. And so this could be, if I wanted to do it for a simple random graph, just nothing else, this would be the set. There are two versions of this. So it could be the set of all graphs with n nodes and a p probability on the edge, or it could be the set of all graphs with n nodes and m edges. Right? So those things are two versions of an Arrow-Schrady graph. And so how do you find those? Right? Well, let's just enumerate them. Right? I'm going to go ahead and write down, generate a pile of graphs of all possible networks that have 1,000 nodes and 10,000 edges, and we'll just see how we fit. Right? Of course, that's impossible. Right? You can't do that because the number of graphs is an exponent. It's not a linear exponential. It's an actual exponential growth curve. And so the number of graphs, the number of unique combinations of graphs you'd have with 10 nodes, right, that you could draw from is over 1 million, right? So you end up with many graphs, and you just can't possibly enumerate them, right? So instead what you need is some way to systematically sample this, right, without having a population to sample from, right? And so that allows us then to come up with a generation process. And once we have the generation process, we can sample, if our generation process is unbiased, right, then we can pull from that a set of networks, a set of samples to compare to our observed. Now it turns out, there's some good news here, which is that if our model is as simple as G and P or G and M, there's a lot of good analytic work. Right? It turns out that in that case, we can actually solve the equations and figure out what the underlying random distributions of most of the statistics we care about are. And so comparing it to a simple random graph is not hard. Right? It's actually comparing it to a random graph where we want to hold some features fixed that is difficult. All right. So we're going to start with the simple case and see where we go from there. So this is just a random graph. Right? So there's nothing there. But one thing I like about the random graph is that there are some things that you might not expect that pop out of a random graph. Right? So you get a Poisson distribution of degree. That means it's going to have something of a skewed tail. And so if I generate a random graph for you and tell you a story about it, and I say, look, this is a high school, look at this, you're going to look at it and you're going to go, oh yeah, Billy over here is really central. He's tied to this other central person. I bet there's homophily on popularity in this school. And you'll tell me a wonderful story because humans are great pattern recognizers, right? You give me a picture, I can tell you a story about it in any day of the week, right? And what you want to do is make sure you're not actually doing that. You don't want to tell a story about how sad old Joe is over here because he has only one tie, when in fact we would expect exactly that if this were just a random generation process. Now there's a deep philosophical question whether if the world were really random, would it still be okay, right? Would it still be interesting? it might be that a lot of random things have interesting context, but for our purposes today, we're going to try to distinguish the random side of things from the actual sort of social process side of things. Hello. And so if you can generate lots of these networks, right? And so this is a simple random graph. It's really easy to generate these networks when you are using the P model. So all you're doing is just saying that I'm going to flip a coin on each edge. When you flip a coin on each edge, the number of edges you get, of course, is going to vary a little bit from run to run. And so the difference between the random graph with a fixed set of nodes and a fixed set of edges is that if you fix the set of edges, then you have to randomly sort those edges around. And that gets to be a little bit trickier than just doing it this way. But in the large limit, when you have very large graphs, it doesn't make any difference. Now, one of the things that we know about random graphs, and this is when I say that we can solve a lot of things analytically, is that there are a series of things that the physicists refer to as phase transitions. And so if you're to flip a coin on a graph with a probability that generates a random degree that's 0, of course no one's connected, or really high average degree, as you move across this set, you end up with some kind of an inflection point depending on the distribution. In this case, it's a very simple Bernoulli graph. And at degree greater than 1, you start to see this rapid shift. And by the time you get to degree greater than 2, you always have what's known as a giant component, right? It's a very steep shift from people who are from a network that's completely disconnected to a network that's completely connected. And if you want to have a lot of fun some point, just to convince yourself this is true, there are a bunch of random graph animations that go through this set. And the intuition here is that if you're randomly adding edges to a graph, you're just randomly sort of tossing them down on the set, your first few tosses are going to lead to a bunch of isolated dyads. And those isolated dyads, by random chance, you're going to, over a few sort of iterations, you're going to run out of isolated dyads to hit. And so then you're going to hit somebody to someone else. And once you start doing this, now I've doubled the size of this component, and somewhere out there I've hit that to another one of those doublings, and another doubling, and another doubling. And before you know it, you get this just rapid convergence, right? And it's really fun to watch this happen in an animation sense, because it moves from nothing connected to everything connected almost instantly. And what's interesting about this from a science standpoint is that it turns out that a lot of regimes fall right on the edge of this, right? So a lot of things that we really care about for disease diffusion or whatever can really be on the balance of one side or the other. And there's probably some deep sort of evolutionary reasons for why that's true. But a really good example was in the early 90s in New York, the men who have sex with men degree distribution was way up here. And so the network was very likely highly connected. As education and AIDS awareness became more prevalent, the degree distribution shifted down below. The HIV prevalence in the city dropped dramatically. New growth through MSM was really, really low. IDU was a little bit more. But then as people got healthier and less worried about and less scared, degrees started going back up. And so now we're on this side of the set, right? So being able to, and so now we have a potential network of MSM in New York, which should lead to a giant connected component, and that's high risk, at least within subpopulations there. But PrEP has sort of made it a little less likely that we get an actual outbreak that we would have seen like we saw in the 80s and 90s. But this is an interesting case where it's not that we live over here in this world all the time, or we live over here in this world all the time. Often we live right on this edge, and if we know where that edge is, we can push people a little bit to one side or a little bit to the other, and you have the kind of things we want to care about. All right. Of course, as it turns out, most of the time our networks are not just a simple Bernoulli random graph, and so we don't end up with this particular curve. We'll end up with but it ends up that there's some randomness in our networks, and so we get a bit of a curve. So what is this? Yeah, so simple random graph is a very poor model for real life. It's not really what I would consider a fair null for most of the observed graphs we want to compare to. And so we want to come up with a fair null, a null that allows us to think about what's driving our network. And so so the goal is to condition on a series of our random graphs on a series of features. We can condition on the degree distribution, the dye distribution, the types of people that they're mixed with, and so forth, and then generate random graphs that hold those features constant. Some of those are really easy, right? So we have fixed solutions for some of these kinds of conditions. A lot of them are not, and we have to simulate it, and that's what we're going to go to at the end. So for example, imagine that I have a simple little network that, not coincidentally, comes out of bad health, and we have what's known as a mixing matrix. So this is a probability that white students are friends with each other, the probability that black students are friends with each other, the probability that others are mixed with each other. We get this kind of random mixing, a little bit more density along the diagonal than in the off diagonals, certainly for whites and blacks, less so with others. And the observed network looks like this. And so what you might ask is that if instead of the observed network, I were to generate a random network with that probability mixing distribution, what do I see? And the network looks a little different, right? So we can do that. We can generate those kind of drawings. So there's some clustering going on in this network, right, that is not going on in this network, even though we're holding constant the mixing in this set. And this, we're not going to be limited to just squinting at a scatter plot to see if that's true. We're going to be able to compare our observed statistics to real ones as we go forward. For example, we can look at the degree distribution for the observed network versus the random network. I think that's, yeah, so the observed is in blue, the random is in red, and we see that they don't match, right? So it was unlikely that our network was generated from a mixing probability matrix of just mixing by race. Some other thing was probably also driving the formation of this network, and our goal is to figure out what that is. Now, it turns out the random graph model solutions aren't limited to just thinking about the density of the graph or the degree distribution. We can also think about different kinds of ways in which these networks unfold in terms of reachability in the network, right? So John Skvoretz has this wonderful, John Skvoretz and Ferraro have a wonderful series of papers that are called bias network papers. This came out of some earlier work done in operations research. And the idea was, if you were to imagine this phase transition we talked about before, that also defines a set of paths in the network. So we know the likelihood that when I reach somebody in the next step, if I do a random walk through the network, what's the likelihood that I reach somebody new? And so what they're able to do in the random graph, you can actually calculate this analytically, that if the average degree in the network were 2, right, you would end up with a curve that looks something like this with some amount of variance around that curve. As the degree gets higher, you can reach more people in fewer steps. And so this is the underlying random graph basis of sort of what we would expect to happen in a diffusion curve. If I were to drop something in the network and have it spread to my neighbors, and then it spread to those neighbors and those neighbors, what happens is that you would get a curve that looks something like this. Now, if my real network has a degree 4, right, then I'd get a much higher spread than if I have degree 2. That's not, that's pretty obvious, I think. What might be less obvious is that you don't actually, if you want to translate this to diffusion as opposed to just reachability, then you don't have to have a graph where the actual degree is 4. You have to have a graph where the transmissible edges degree is 4, right? So if I use a condom every time I have sex, then my degree is 0 in a sexual network, right? But if I have 2 people that I don't use condoms with, then that creates a different set of curve than if I have 4 people I don't use condoms with, even if it's the case that there are 100 people that I'm having sex with, right? So the idea is that we can think about an effective degree as opposed to an observed degree and still get these kinds of curves. Does that make sense? Once you have a random model for what this looks like, you can then compare that to an observed network, right? So this is what a set of trace curves looks like in one observed school. We fit the random graph model to that reachability curve that we would expect in this set, and we find that the observed network tends to have much lower reachability than a random network. Why is that? What's the intuition for why does it take longer to reach everybody in an observed and in a real world network than it might in a random network? Yeah.
You have factors like homophily or local clustering that limit your interaction with other people.
Right, so what's that doing? What's homophily and local clustering doing?
It's making it so you're more likely to interact with certain types of people or similar to you, but when you do that, then you're going to have less ties to the entire network.
Right, and less ties to people outside your set, right? So what this random network is doing, it's saying that let's start with an individual, go to the one step out, right? See who do you reach. Go to the next step out, who do you reach? Next step out, who do you reach? Next step out, how do you reach? In a random network, the only thing governing the probability that I meet a new person is degree. And so if every person on my network has a probability has a degree of 3, then in a really large network, I reach 3 people in one step. It's very unlikely in a random network that those 3 people know each other. So I'm going to get out to 9 people in 2 steps. Right, you see where this is going. You get almost geometric growth. You only get cross ties at random, which is going to be really low. So these curves move really quickly because you're effectively reaching new people, a lot of new people at each step. And the number of people of recursive edges, the number of edges coming back on the people you've already met, is relatively low. Whereas if I have homophily, right, if I have the distinction between black dots and white dots, then it might be the case that I have a much more likely to go for those, and these guys are much more likely to go to each other. And so you've lost this number of random ties going out into the population. Instead, you're recapturing the people you've already set. And so if this sounds familiar, this is exactly the idea behind capture-recapture studies, right? So if you're over in ecology and you're trying to figure out the size of a population of muskrats or something, you go out, you catch some muskrats, you tag them, you put them back in the population, you see if you get them again, right? And so this idea is that if you want to get back to you can think of this as a capture-recapture problem of people walking through a network, right? And so it defines an underlying clustering that is the diffusion space of the network. Now this is actually, these reachability curves are defined on this notion of a breadth first search, the 6 degrees of separation kind of idea, that I go from my friends, all of those friends, all of those friends, and all of those friends. You could do the exact same thing with a random walk model. Right? So I could say, instead of having the idea that I reach all of my friends at step 1, all of their friends at step 2, all the unique new friends at step 3, I couldn't say, what's the probability of reaching a new person if I flip a coin randomly amongst my sets and just do a random walk through this network? You'll get a lower curve, right? But you'll still get this kind of sinusoidal curve going over another set. That defines a slightly different social process. But again, then I can compare an observed network with that social process, a random walk social process, to a random graph and get a sense of how different my observed network is to a real network. And so we can think about this as an ulterior set of models, and this is something that was showed that Molly was showing a couple days ago. Was that a couple days ago already, or was that just yesterday? That was just yesterday. Wow, there's a lot of material in one day. makes my head spin. And so they have this notion of a small world graph that Duncan Watts introduced in 1999. And the thinking is that what we observe in these real world networks is this high local clustering, right? And so in a real world network, people are clumped into groups due to homophily or focal organizations or something like that makes it hard for them to reach each other. What would the epitome of that model look like? It would be something like this, where everybody has their own groups. We have the sociologists, the economists, the physicists, the statisticians, and no one talks to anybody else except for a few people who create a bridge just so the math works out. If you then add a little bit of random noise to that graph, you end up making it much, much easier to reach everyone else. And with the actual definition of a small world graph are graphs where once you control for the random reachability, the length of the ties between people are relatively short. That is, it's easy to reach people quickly relative to a random baseline, but it's much more clustered than you would expect given the random baseline, right? And so there's this whole class of networks out in the world where this feature is true, where it's easy to reach lots of people given the distribution of path lengths in the network, the number of steps I have to take to get between nodes, but they're nonetheless much more clustered than I would expect given a random graph with the same degree distribution or something like that. And so these kind of graphs, it turns out, are really interesting because they're a nice toy model for a lot of social processes because they have the same kind of diffusion processes if you in simulation and right assumptions, and they also have they seem to be ubiquitous. Like a lot of graphs out in the world have this feature that they're more clustered than you'd expect by chance, but still have shorter paths. And the reason for that, going back here, is exactly because of this. Actually, it's just because of this. That it doesn't take many random edges to create a really quick shortcut, right? So if all of my edges were caveman edges, except for 2 at random, I still reach 60% of the population in about 8 steps, right? And so you end up creating a small amount of randomness in an otherwise very structured graph allows you to reach everyone else in the population. Now the flip side of this is that, and there's a whole debate that we don't have time to go into today, is that there's another real problem about the reason people like the small world graph isn't because of this feature. I mean, the reason people like the small world problem, they find it interesting and stuff, isn't because of this feature, right? It's because they can think through this feature, right? So I can say, I'm going to give you 2 actors, like tell me like the sequence of movies that gets me from one actor to another. That's a really interesting problem. And if the world really worked the way this model said, if there was a little bit of truly random connections between that, very few people would be able to do that, right? And so what's interesting about real world networks isn't that they have this characteristic, it's that they have this characteristic and they're searchable, right? And it's possible for informed actors to navigate through that network and find something that's pretty darn close to the shortest path between the 2 nodes, which wouldn't happen if ties were perfectly at random. And so what that means is that the thing creating the shortcuts between these networks probably aren't actual random edges. They're probably things like I went to high school in one place and then moved to college, and that creates a set of knowledge about where I was at one spot and at another, but also bridges between lots of people that are not otherwise there. So what this result returns on, the substantive version of this lower clustering but the ability to reach people eventually turns on, is not the actual randomness, but the distribution of bridges are random enough to have this shortcutting feature. Does that make sense? It's a little bit of, I'm cheating a little bit from myself in the next session, but there we go. All right. So going back to comparing observed statistics to random statistics, this is the Triad Census we talked about before, which is a nice way to summarize a network because it's in the Triad Census ends up being a nice structural hashtag, if you will, for a network. And so we can take our observed network, see how many triads across the distribution they are, and compare it to a perfectly random graph. And so comparing it to a uniform random graph is pretty uninformative. It turns out that in this network we have 5 completely closed triads, 12 triads that have 5 arcs in them, right? And that is something like 21,000 times more than we would expect by chance, because the random probability in a network of this size, where you're getting a closed triad, is really, 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 really low. And so what we can say is we observe a lot more clustering in this network than we'd expect by chance, but we still only have 5 clustered triads, right? So we want to take this maybe with a little bit of grain of salt, and this is just highlighting the point that a purely random network is a pretty poor model for social life. So instead, we might want to condition on something else. So we can take that same network, and we can compare that to a network where we've held constant the number of null dyads asymmetric dyads and mutual dyads, that uniform mutual asymmetric null distribution. And we can say, compared to what we would expect given that distribution, given that we're going to fix the number of mutual asymmetric and null ties in the network, we find that we have about 9 times more than we would expect by chance. Still more than we'd expect by chance, but not something like 20,000 times more than we'd expect by chance. Right? Do I care about that? Yeah. So this is the Triad Census. I love the Triad Census. I consider this the actual periodic table of social elements. This is the thing that generates social behavior. That if I have a theory about how a person behaves relative to other people, I can map it on to a network, to a distribution of triads. But that's an entire another lecture that I don't have time to go into. But we can compare for all the ad health schools, all 200 and so, 170 some schools. We can compare the likelihood that we would observe the number of triads we've observed in that network compared to this random uniform distribution. And we find that we get a lot more of a certain set of triads than we would expect by chance. So this O3OT triad is that a friend of a friend is a friend, and we observe that many more times than we'd expect by chance, right? And so this is part of the idea that a friend of a friend should be a friend, where we tend not to observe this purely cycle that I'm a friend with you, you're a friend with them, and you're a friend with me, but there's no reciprocation in there. That rarely happens. We're exceedingly unlikely to find the case where we have 2 really close friends and no friend between them, right? So I like my high school roommate, I like my wife, they don't like each other. Like that pattern doesn't happen very often. In fact, we have negative selection on that pattern. And so this gives you a hint for thinking about how to think about social processes. So you take a look at your network, you say, you know what? I have a lot more of these kinds of triads than I have another kind of a triad. What social process might be accounting for that? And it sort of helps you build an intuition for what might be there. I'm going to have to go into that. It's too much. All right. So it turns out, of course, that what we can condition on analytically, and that's what I've been showing you thus far, are relatively simple substructures. The distribution of dyads is a nice way to soak up some of the variance in random graphs, but it's not it's far from what we'd like to count for substantively in a setting. In particular, we might like to know about the degree distribution, and not just the expected degree distribution, which we can get pretty well, but the actual observed degree sequence. So for any given network that I've pulled, person 1 has a degree, person 2 has a degree, person 3 has a degree. I know what that actual observed degree sequence is, and that actual observed degree sequence is going to constrain the distribution of things in the network. So for example, if I have a network that has 10 people, has one person that has a degree 10, that person is always going to create a star of 10 in the network. And so the only question left over for random chance is how these edges are connected to each other, right? So there's always going to be a hub with 10 nodes in it. Like that should be in my network. And because of the random happenstance that I have a person with a degree 10, I might get a lot of close triads because the only thing left over is for people to send ties amongst those sets, right? And so we'd like to be able to figure out if there's a way to compare a random graph with the exact same degree distribution compared to the ones we don't have otherwise. And there are a few of the ways to do this. The most common way to do it is this notion of edge stem sorting, right? So what you do if I have if my degree distribution is that person 1 has there are 2 people with a degree 1, 2 people with degree 2, 1 person with degree 3, then I can say, well, we're going to call the person that has degree 1 A, right? He has a stem out in the universe. Person B has a stem out in the universe. There's people with degree 2, so C has 2 edges, D has 2 edges, and F has 3. And then what you do is you just sort these together, right? And so you have to be a little bit careful to make sure that C doesn't connect to themselves, or that if you don't allow it, that C's connect to F's twice or something. So there might be some constraints on this zipper method depending on how you do it, but essentially you take half of your volume of edges, you put them in one column, you take the other half of your volume of edges in the other, and you randomly sort them and zip them together. Now, this will generate random networks that have a lot more structure than a real random network, than a uniform random network, because they are taking care of these hub networks. So this is a version of a commercial sex worker network and a commercial sex work network that Giovanna and I put together using this method. And you get commercial sex workers as these hubs, and their johns are out there in the edge, and so you get a very strong mixing heterogeneity by degree because we built that into the network. Now it turns out that this, now I'm pointing this out as an exemplary way that you go about doing this. I want to be really clear that you shouldn't go out tomorrow and write yourself a 4-line algorithm for doing this, because it's really easy to get this wrong, right? And the ways you get it wrong can create biases in the comparison set. And so it turns out, for example, in this case, that to make this work, you need to make sure that you don't have these C tied to themselves. Just you say in the real world we don't allow self loops. In this random world, I can easily allow self loops, right? And if I have a small network, I'm going to get self loops a lot. And so what that's going to do is create a biased set. I'm going to have one observation in my network that is impossible in the set of networks I'm trying to compare to. And so that means that I'm comparing my network to a biased set of randomly generated networks. So you need to be really careful about how you generate these random networks. And so the intuition of this zipper idea I want you to take home, but the actual algorithm is not just zip. You have to have a rule for how you connect it. One simple rule is do a simple zipper, and every time you get a violation of the world, throw that graph away and start again. And that will give you a uniform distribution of graphs over the sequence of all observed degree sequence. It'll just take a lifetime to converge, because you're going to throw away 90% of the graphs you generate. And so there are smarter ways to do it than that. In practice, it matters a lot for small graphs. You get a graph around 1,000 nodes or bigger, it's not going to make a huge difference in most of the things we compare for it, but you still want to be careful about what you're doing. Right? Sensible? See where we're at? See where we're going? All right, now again, what we've done here is we've generated what I've talked about thus far is ways that this kind of a model is an intuitive model, in the sense that what you're doing is you're constructing via simulation a comparison to get your observation to. And you can do that in any kind of way you want. So I could do the degree distribution like this. I could say that I also want to do mixing, so I'm going to make sure that I have a color on these edge and a color on the nodes, and I'm going to make sure the color-to-color mixing is exactly what I observed in the distribution. And so I do my zipper within each of the cells of the mixing matrix, right? And you can make that mixing matrix as complicated as you want if you want to get complex heterogeneity and mixing and so forth. The problem is that most of these algorithmic approaches really require you to write a really careful algorithm, right? And writing really careful algorithms is really hard. And there are some really good ones in computer science that we can steal, but by and large, these problems are the more things you want to condition on, the more difficult it is to get the conditioning right. And this is what takes us into the realm of a different way of thinking about this problem, which is to go back to the a random graph model and then think carefully about the differences between cells in an adjacency matrix. And that's where we're going to go next to try to get a parametric form of this model as opposed to a simulation version of this model. We'll still have to use what's known as an MC-MC chain to walk through that parametric set, but it allows us a much more flexible way than trying to hard code these types of simulations. So that's where we're going to go for building the networks. But first I want to take a sidestep and think about this randomness, this comparison to randomness with respect to observed variables. And to do that is this notion called quadratic assignment procedure, or QAP models. A QAP model is a way of taking this notion seriously that I've observed some setting and I want to compare it to the same side of setting but where the world is random. And you do that with a random permutation test. And permutation tests I love permutation tests because they just make the world so simple. And you don't have to make any assumption other than that you've done the permutation at real random, right? And that's a lot easier thing to do than to figure out that I've actually zipped all my edges together right. And so permutation tests are non-parametric. They have a really nice way of being able to compare an observed real world thing to a process at random, where you've defined that process at random very clearly. And so they're very powerful in that way, and they don't require a huge number of assumptions on the part of the actor. And here's how it works. And so what you do is you imagine I have two adjacency matrices. I have families that marry each other, and this is in Florentine, Italy. And I have families that do, and those same families do some business with each other. And it turns out that the correlation between whether you marry a family and do a business with each other is about 0.38, right? 0.37. And so it's the case then that we want to know, is that correlation big or little? Right? And in order to do that, we do it's known as the dyad-wise correlation. So we take each cell of this matrix, usually excluding the diagonal, but it doesn't really matter in this case. And so we compare each cell of the dyads to what they are here. Now I have a simple dyad array of my data set. I have a correlation then between the first column and the second column. That's all this score is. Right? So a matrix-wise correlation is just a correlation on the dyads where we've included all dyads. And what we'd like to know is whether or not that's a big number or not. And so in order to get that, what we do is we permute the original matrix. So this is what we've observed in reality. we take that matrix and we just randomly resort the orders. And so now instead of having 0, 1, 2, 3, and 4, we have 0, 3, 1, 2, and 4 because we've randomly switched the rows and columns. Now you've got to randomly switch both the rows and the columns simultaneously, right? You can't completely change it out, so you got to make sure you do both things right. But if you randomly permute this, now I have a really nice permuted network. So this is a process, this is a network that's been generated at random. We know the process is random because I just randomly juggled it. But I've also maintained all of the degree features. Right? So all of the marginal distributions stay the same, the density stays the same, the dyad distributions stay the same. Like all of these features stay the same. But I've just broken the association between the marriage ties and the business ties, for example. Right? So it's a very simple way to get at this solution. And the algorithm is boneheadedly easy. Right? So you calculate your thing you want to do. For as patient as you want to be, you randomly sort the matrix, you redo the correlation, you store the outcome, and you compare one to the other, right? So it's a very simple thing to do, and it ends up, in this case, that if I do a bunch of random permutations, 500 random permutations of that little network, compare the observed distribution to my observed distribution to the random histogram of distributions, you'll see that, in fact, it's very unlikely to observe this high of a correlation if the process were random, right? Now, it's also the case, right, that the process at random, like a random permutation, is again a pretty low bar in some sense, right? And so what you'd like to know is and for a pairwise correlation, it turns out, I've done a lot of these QAP tests, the mean of the QAP is often very close to 0. So you wouldn't have gone too far wrong. The variance is where you end up being fairly different. Clear what that is and how, intuitively? How am I doing on time? Half an hour? Awesome, great, because we got to get to the meat of this thing. All right, so this is easy to do. UCINet is by far, I think, the best tool for doing QAP models, and what's nice is that you can do it for multiple regression of any kind of dependent variable as well. So imagine I have some network, and I want to figure out whether being friends affects an outcome of some sort, but I want to control for the fact that whites tend to be friends with each other, and same gender tends to be, for race homophily, and for gender homophily. And so what you can do is you have your network, then you create a similarity matrix. Any kind of similarity matrix you want. Usually it's something like same race or difference in education or something like that. And then you do that same kind of correlation trick where I have some y variable, but in this case I turn that y variable, like how rich you are or some such, into a distance variable, right? So then I create a distance between each pair, which is in this case just the absolute value of yi to yj, and then I do that exact same QAP trick, but instead of doing it for a correlation, I do it for a multiple regression. And the nice thing is that UCINet does this for us. It'll do it across a whole series of different types of models. So I can do it for correlations, I can do it for multiple regression, I can do it for logits. It's a really powerful set, and one of the nice things that Steve has done well, and his team has done well, is that you can write this algorithm to do it yourself, like in the brute force way. But logits are themselves an iterative process. If you wanted to get it like 1,000 draws from a permutation test, it'll just take forever. And so, but they've come up with ways to optimize this, which makes it run really fast. And so you just pluck through the set, and you get a very simple sort of set. So in this case, the model fit, we got an R-square of about 0.54. We see that being connected has an unstandardized coefficient of about 0.17. Sorry, this is so small you can't see it. But the likelihood of seeing something as big as that it just never happens, right? And so the p-value in this is 0.006, which means that we almost never see an association this large, even after controlling for the other things in the model. Right? So it's a very nice, simple, clear way to figure out if there are associations beyond chance. So we're clear on what QAP models are, because that's all we're going to get. Jamin's going to give us some examples to it later this afternoon. Awesome. All right, so now I want to switch gears again and go back to this idea. So instead of generating a random network, we want to think about how do we model a network parametrically. And we do it by thinking about this distinction between a random graph, right? And so if we imagine that we have an observed network, in this case, a very simple small network. The diagonal we're going to leave blank, we don't care about it. And we've observed some set of ties on the network. What we'd like to do is say that this observed network is a function of a series of features on the network. In this case, it's a function of the overall density of the network, of some features about the rows of the senders of the network, the columns of the networks, and the dyads of the network. Right, so this is as simple of general a model as you can get. And to give you an idea about how this works, let's imagine that these coefficients are all 0. I just have an overall density parameter. What that's saying is that the probability of this matrix is completely uniform. Right? And so that's the model we're fitting when we say compare the observed network to a uniform random graph. Right? And this is, I'm trying to build an intuition from where we were before, because we're going to blow it up in a second. So when I compare a network to a uniform random graph, what I'm doing is I'm comparing a network where I have a constant density everywhere in the network, and my observed cells just happen to pop up from time to time. Well, now let's add a little bit of variance to this model. What I could do is I could add row effects. Right? So I could add the degree of the row. This is a row normalized degree matrix. So in this case, every person that has 5 observed rows is going to be the highest probability. Their probability of having a tie in this network is just over 0.5. Whereas if I only have one tie, the probability of observing a tie in that network is 0.13. Right? So all we've done, just to be clear, is we've taken a simple uniform mixing idea, and we've just matched it now on the rows. So now this is a uniform random graph with a fixed row model, a fixed expected value on the row. And this is a version of the configuration model. So in this case, we can solve that analytically. It's no problem at all. We literally know the expected value. We can calculate a bunch of these. It's not hard to get. Right? We could, of course, flip it around, do the same. We can do columns, right? So that's not hard. You guys see where this is going. Right? This is not a deep generalization problem. Or I could look at both marginals simultaneously, right? And so now I have a set of probabilities that are based on the row marginals and the column marginals. This is exactly the configuration model. So in this case now, I know the expected value of a tie in each of these cells, given the degree distribution of the columns and the degree distributions of the row. And that does a pretty good job, right? Here you can see that these, the bolded cells are our observed ties, and the bold ones tend to be red, and the blue ones tend to be not bolded, right? So that tends to be a nice set that there's a lot of this network that is driven entirely by the marginals, but it might also be the case that there are features of dyads themselves, some kind of dyadic similarity that in this case is driving the outcome, right? And so that allows us to put a little bit of finer point. And this is the intuition behind an exponential random graph model. Right? So this is where we're going to go to try to do this. We're going to have some features of senders, some features of receivers, some features of dyads or collections of dyads that help us sort of narrow down this marginal correction effect. And it turns out that estimating this part of the model, like just fitting a logit to this or something, that's easy, right? Estimating the standard errors on these suckers, that's a hard part. So getting the variability of the set is what's hard to do. Like this is literally, when we get to the end of the day, this is going to be a logit model. So the actual estimation on the coefficient values tends to not be that hard, but the estimation of whether or not those coefficient values are big or small compared to a random, to the class of all graphs in the uniform set, is the hard part. And so that's where the MCMC comes in. Are you tracking with me thus far about what the task is? Awesome. Okay, so the model works pretty well. It misses in some places, right? So and this is going to become important later. So here we have some ties that this simple model didn't fit. It also overpredicts in other places, right? So we predict a tie here, but we don't get it. And so a huge amount of work that's gone on in the literature the last few years is to figure out essentially how we fix that problem. Because in theory, this model should work really, really well. In practice, it still misses a lot, right? And so why is that? And it's probably because of either we have a poor model specification, right? We just didn't specify the social process well, or we have a poor model estimation set, right? It's like the model's great, but we have a crappy MCMC chain and it doesn't go through where we need to go. So we're going to see how we get that. Right, so in order to get here, we need to, so the model I just showed you was a variant of what's known as a social relations model. And this model has a long history. And where this model essentially started at, the piece that we really sort of kicked off this work in the social sciences was what's known as the P1 or the P2 models coming out of Holland and Linhart in the 70s. And what this model does, it says, let's take that adjacency matrix we saw, ties between I and J, fit it as a logit. Everyone knows what a logit model is, right? This is, okay. If you don't, talk to someone in the back, they'll help you out. And what we're going to do is we're going to fit a model where we have row effects, column effects, and reciprocity. But the key thing to pay attention to this model is the subscripts, right? So I'm going to have a different row effect for each person, a different column effect for each person, right? And a single row effect, right? So in this case, I'm fitting 2n plus 1 parameters to my model, right? That's a lot of parameters, right? Just so you know. I have n squared data bits, right? So that helps, n squared minus 1 data bits. So I haven't saturated the model. But this is still a lot of parameters. And so we'd like to find a way to simplify our model. But in theory, this is kind of nice. You can fit that model. One of the things that I really like about the simple P1 model is that you get these fixed effects estimates. I get an estimate of this coefficient, right, for each person. Right? And so what this is how expansive you are, how much you would like to sensitize, or how much we'd expect you to sensitize. This is how attractive you are given the volume of the network, right? So we would expect you to have a certain amount above and beyond what we get from your degree. And what's nice about that is you can then compare that to your actual degree, right? So some people are much more expansive than we would expect given the number of ties they sent. Other people are much more attractive than we would expect them to be given the number of ties they sent. So this is a nice way of being able to sort of net out perhaps some kind of a random version of what we'd expect from someone from the actual version. All right, but that's the simplest set. And what's happened in the model, and this is sort of what we've talked over time, is that these models just got generalized. And so we've moved from having a simple reciprocity effect to now having a group-specific reciprocity effect, or having some node attributes or something. And that's where we're going to go with these models. The problem, of course, is that statistically, the standard errors that just come at random out of the out of your favorite stats package are assuming that each of these observations, each of those dyads are independent. And so the nice language they use in the literature is that the standard errors are approximate. They're really approximate. So you got to be a little careful with that. So how do we fix that? Strauss and Ikeda came up with a really nice formal mathematical model for this that solved this problem. In the first paper was the original first paper was in the late 70s, but it got picked up again in the mid 90s, early 90s. And it takes a slightly different way of thinking about it. So I want you to just wrap your head around this for just a second. And so what we're doing is I don't want you to, for just a minute, don't think about dyads. For right now, think about whole networks. And so what we're going to do is we're going to ask, what's the probability of observing our particular network, given that it's a subset of the class of all possible networks, right, defined by a set of statistics on observed features of the graph? That's what we're doing. And so given that I have a whole universe out there of graphs, right, I've observed one observation. Remember, that's my inference problem. I've observed one observation. Out in the world is a class of all networks that have that set, right? And that set is defined by the fact that I have a set of summary statistics on the network and parameters that describe that summary statistic. And in order to make this a probability, I have to normalize over this set of summary statistics. So that is, I need to know how many graphs have this statistic. And that's the really hard part, right? And so this simple probability would literally just be a little bit of arithmetic if I knew that there were 1 billion graphs of this particular configuration in the population. Then I can compare the observed set to it, and I'd know exactly what I have. We can't do that because we can't actually enumerate that set. So the entire trick is figuring out how to enumerate that set. And the trick to doing that is to come up with this little thing called a fiction. That's not a thing. This little fictional thing called a graph complement. Now, this is a little hard for people to get their heads around, but you remember how you learned this little trick in high school algebra, where if you needed to get your equations on one side or the other to balance, you might do something like add 1 as the fraction of something over itself. That way you can take part of it and put it on one side and part of it put it in the other. That's the kind of trick that Strauss and Ikeda came up with, right? And they do this by saying what we're going to do is we're going to model the probability of a tie between these folks, right? This is just another way of just writing logit. So the probability of a tie between xij conditional on this thing called the graph complement, right? And so that conditioning you're never actually going to see, right? But that's the equivalent of one of these fractions that you don't have in front of you, but you used in order to multiply both sides of the equation by 1 so you can get the algebra to work out. And so in order to get there, he had to invent 2 other bits. So first you have the socio matrix, your adjacency matrix, where you force the tie to be 1. You have the same network where you force the tie to be negative, to be 0 in a binary case. And so then we had this complement, which is the network just without that element. So it's everything else held constant except that single element. And so then if you do a little bit of algebra on these sets, it turns out that you can express this entire probability, the probability of the graph conditional on the complements, right, as a function of a series of change scores that has to do with the tie being present or absent. And that's a brilliant move, right? And it's really hard to overstate what a great statistical trick this is, because what it allows you to do is now I get my logit model and look what I don't have anymore, right? I no longer have to worry, about this guy, right? The normalizing constant falls out. That's what this allows us to do. Essentially, the normalizing constant gets soaked up into that complementary set and goes away, and I can now estimate the graph, unbiasedly estimate the graph, right, as a function of these change statistics. And this is what has sparked the entire ergon revolution, is the idea that once I know this, now all z of xij plus is some statistic with the edge present. I subtract that same statistic with the edge absent. I do that for all dyads in the network. That creates a single dyadic vector, which is the change score, and that change score becomes my regression model. Now, to prove to yourself that this is true, imagine what the change score looks like for the simplest possible network statistic, which is a tie being present or absent. Right? So if I force the tie to be present, what's the xij value? It's 1. I force the tie to be absent, what's the value? What's the difference between 1 minus 0? It's not a trick, right? It's 1, right? Now, what's that difference look like for all dyads in the network? It's not a trick question. It's like 1. If I regress something on a vector of 1s, what have I fit? An intercept-only model, right? So your intercept is just this notion that say there's an edge here, right? So if the statistic is there an edge, right? That creates a 0, a 1 minus a 0. It creates a vector of 1s in that dyadic regression. That is the intercept of every logit model you've ever fit. And so the intercept gives you density. That's all it's doing, right? And so the change model recovers this thing that you would have put in the model anyway, but didn't know how to interpret. And now you know what that model is actually doing is recovering the density of the graph. And we're going to do that now so if Z is edges, that's pretty stupid. Like it doesn't have any really strong, other than density, doesn't mean much. But it could be reciprocity. So what's the number of reciprocal links in the graph if this tie is there, if it's not there? It turns out that number is going to be 1 every time J nominates I. It's going to be 0 every time J does not. So essentially the mutuality parameter becomes a dyadic indicator for did alter nominate me. And so these change statistics for the simple dyadic things become easy to see. So the number of people that are same race, for example, is going to be, if this is a same race statistic, then xij is 1 if I is equal to j in terms of their race. So it ends up being a dummy variable for whether I'm the same race as you are. And so for dyadic independent features, these become really simple intuitive features. For non-dyadic features, if it's the number of triads in the graph, the number of closed triads, this calculation gets both a little more computationally intensive and a lot harder to interpret intuitively just looking at the dyad score, but it means the same thing, right? And so this is why it's a really great trick to get to. Are you following where we're at? I'm kind of geeking out on this because I think it's such a cool thing, but trust me, it lets us get to where we need to go, okay? All right. So here's the steps in fitting one of these models. So the steps in fitting these models, you specify your model, right? You fit the model, you figure out whether the darn thing converged. If it's poor, you do it over again. If it's not, you publish your paper, right? So that's how this model works. You get tenure, you become a famous person, and you tell about your day. So specifying the model, it turns out, is a bit of a pain in the butt. And to specify the model, we have a series of terms that are those Z statistics, those things that we're going to do the change scores on. And intuitively, we just have a bunch of them. There are a few of these are easy to make sense of, right? So if you have a theory that is sort of well known in the field, we can match it to a set of terms. And this is probably the thing that makes ergms most flexible, is that it's really designed to be an operationalization of structural theories. And so if my theory is homophily, that birds of a feather hang together, then essentially what I'm expecting is that green nodes hang out with green nodes and yellow nodes hang out with yellow nodes. And so I have something called a node match parameter in the model. Right? If in the set I have a friend of a friend is a friend, or an enemy is an enemy, then that's a balance or a transitivity feature. If I have something like the small world notion, then what I'm really going to do is I'm going to specify a model that has a lot of clustering and a short path set. And so I'm going to have 2 parameters in the model, at least, to try to capture this small world feature. But I can do that because a small world is defined by having both high clustering and low path length. I put those in the model and see what pops out of it. If I'm thinking about a preferential attachment, that the rich get richer, there's going to be this star sort of notion, then I'm going to have an in degree, or what's known as a k-star, sort of parameter in the model that have lots of people getting lots of ties, right? So these are ways of thinking about a model. And what's brilliant about this setup is that if you can think of a theory that you can then map onto a pattern, you can specify a change statistic, right? So anything you can think of, you can do. And the way that ergms are set up is that in theory, any of us can write these packages to do this set, because all you got to do is calculate the change statistic. But so I have a bunch of these in the set. I'm going to get through them here really quick. And I want to point out one thing about model specification, which is that this ends up looking a lot like a logit model or a regression model. And we tend to have an intuition about how parameterizing logit models or regression models work. In particular, we tend to think that if if we have a positive coefficient on something, that means we get more of that, and that's fine, right? It's not that big a deal. In these models, it doesn't quite work that way. What you're really doing is you're specifying a return to a change in the network. So that's what these change statistics are doing. So you're saying the marginal return to a change in that network is generating a new higher or lower probability of an edge. So for example, if I have a theory about transitivity, right, so I think a friend of a friend should be a friend, that means the more close triangles I get, the higher likelihood of probability in my graph. I know that my network is transitive. I know that friends of friends of friends in my network. And so from my intuition from regression is that if you're a rich person, you have high education, that means that I would expect fit a line through that, it should be fine, right? The problem is that what you're really doing is simulating an edgewise process in the MC-MC chain under the hood. And so if the theory says that some of this is good, if we expect to see closed triangles, then every time we've created an open triangle in the underlying network, notice you've created the opportunity for closing another triad, so let's make more of them, right? And so if this is good, this is better, and the simulation is going to quickly take you to a snot ball, right? And so when you think about what's really happening in your network, it's not the case that all friends of friends are friends, right? It's the case that most of my friends of friends are friends. And there's some marginally diminishing return to the number of friends that are friends because I have an energy constraint. I can't be friends with everybody in the network. And so in fact, what you really want to do is specify your triangles term to have a curved effect, right? So that an early set of this is important, that I like to do this, but because of an energy constraint as a human critter, I can't possibly make friends of friends of friends of friends with all my friends of friends of friends of friends. And so I have to have some diminishing marginal return. And that's what creates this notion of a GWES parameter, the geometrically weighted edgewise shared partner. It's an ugly term, but this is essentially saying the functional form of closing triads is diminishing marginal turns as opposed to a simple linear return, right? And this is the kind of thing that we only learn because our models fail miserably when we specify them poorly, right? And so the reason we discovered this set, once you know it, it's like everyone says sociology is obvious. It's obvious once you know it, right? And so once you know that this kind of a model is stupid because what it's implying under the hood is that everything should be either a clique or empty, right? Then you think, well, how do I avoid that from happening? Well, I change the functional form, right? That makes sense. But do you have a good intuition about 4 cycles in sexual networks? I don't, right? And so I might have a little more of it than some of you, but we wrote a paper on it. But the idea is that there's this idea that, that most of the time our intuition that we borrow from regression, that a little bit of X is good, a more of X is better, that kind of linear sort of return doesn't work in these models. And so you need to really think about this as using a parametric approach to simulate a network. Time? Okay. But 2.5? Oh, awesome. Awesome. I've never been in that situation. All right. We might actually have a chance to talk to each other and have some coffee. How do you like that? All right. So how do you run these models? You run these models using the StatNet package in R. Quite honestly, this is part of the reason that R has become such a dramatic sort of tool in social network analysis nowadays. It's because all of these tools are developed there. And it's developed there because a lot of the work in the MC-MC chain analysis and some of those things are coming out of, and optimization are coming out of the computer science literature that started using R. So this is how we ended up in that set. And so the model really does look like any other linear model specification you might do in R. You specify your model, it's an ergom object, you have a network as a function of a series of parameters. And the results look something like this, right? So I have an edges parameter. Your edges parameter is always negative. These are interpreted, or almost always negative. These are interpreted on a log odds scale, right? So this is, if you exponentiate that, you get the probability that you have of observing a tie-in in the network. And it's negative, not because you have a propensity against edges, it's because your density is less than 0.5, right? Most of our networks are sparse. And so this is, once you exponentiate that, you're going to get your density of the network, and unless your density is greater than 0.5, this is always going to be negative, right? So it's just a simple way of seeing that. So people often overinterpret the edges parameter. It's the model intercept, right? So just remember that. In this particular case, we find that there tends to be a higher than expected likelihood that people are linking if they're in the same grade, if they're the same race, and if they're the same sex. All of these things are generating connectivity in this particular network. Now, because it's under the hood for these non-dyadic independent scores anyway, this thing is an MC-MC chain, it's worthwhile for you to spend a little time looking at your MC-MC diagnostics when you run these models. For those of you that don't know, the 30-second summary on what an MC-MC chain is that if you remember your old style input-output models from probabilities, so if I have a row thing, it predicts a column thing, I go to a row thing, I predict a column thing, right? So you get, the model should converge at some point on what's known as a mixing space. And what you're doing in an MC-MC chain is you're taking this big space of models, of all possible models that are out there, and you're walking through that input-output chain probability space. And so I take a step, I end at one spot, I take a step, I end another, and you're sort of doing a hop through this spot where in each of the case, say something like this, if I were fitting this model, I start with a value of 3.06. And then I take a step now to keep everything the same to go to 3.08. Or I hold this where it's at and I take a step in the space to move this model up or down a little bit, assess the fit. And so at each step of the chain, what you're doing is going through and trying a slightly different parameter as you walk through this space. In doing that, what you hope to see, if the model is converged, you're essentially, you're at the spot where you need to be and all your steps are random. You're not doing anything systematic. If instead these chains are highly correlated, that means I'm going off in one direction, right? Instead of having this nice little bristle brush through here, what you're going to have are some kind of curves and patterns. And that tells you that your chain isn't mixing well. It means you're in a part of the parameter space where it's really hard for the estimate to get to converge on something stable. And so that's a bad problem. That's a really strong indicator that you have a poorly specified model. You need to go back and fix your model. Okay. The nice thing about this model is that what you really have done is you've generated now a model version of that funky probability table I showed you before with the blue and red squares, right? And now once I have that probability table, right, under the hood, that's stored as an object, I can sample from it. I can do a posterior draw from the distribution of all networks implied by my model, and I can simulate as many networks as I want. And this is exactly what we do, right? So once we have this set up, it's literally as hard as saying simulate the model I just connected with as many as I want, right? And so once I do that, I can generate a random version of my network. And it turns out that this turns out being a really powerful feature of the network. Because once you can do this, once I know the probability structure of my underlying graph parametrically, I can then change some of these things. I can say, what would happen if there were no homophily on race? What would happen if all the ties that I see are missing are fit the exact same way as the ties that are not missing? That is, if my missingness is really at random. Well, I can just fill in those NAs with this simulation, right? And so there's lots of things you can do in terms of scoring and simulating that allows you to take the network that you've observed and extend it a little bit into if-then segments in ways that are much simpler than trying to come up with a zipper model for edges that doesn't lead you to a biased space, right? Okay, so with that said then, what's the one thing we do a lot for simulating networks from ergo models? We use that as our primary assessment of the goodness of fit of the model. And the logic here is that if I've specified the model correctly, right, if I have all the things that are social processes that are fitting the model, anything else left over should be random, right? So we're not denying that there's randomness in the graph we've observed. It's just that anything interesting about that graph is captured by whatever social process we put into our parameters. And so by capturing those two things, we're able to then say, let's simulate a bunch of networks and compare it to our observed networks on some observed statistic, right? So in this case, we have the degree distribution. Our simulated networks have on average have this kind of distribution of the degree distribution. Our degree distribution fits within the confidence intervals, but that's not a very pretty fit, right? It's not the right functional form. We simulate way too many nodes that are isolated in this network compared to what's observed in reality. Way too many nodes that have a value 4 compared to what's observed in reality. So this is telling me that I want to go in, and ideally this black line would follow the same set here. Like if I actually fit the network, I should be able to simulate the features that are left from it. Should just be random noise. And that means, and if that were true, then things that aren't in my model, right, should be able to be captured the same as the things that are in my model. Does that make sense? And so for here we have the edgewise shared partners. So this is the number of closed triads in the network. Right, we're doing a rotten job of this. Right, so the model is predicting almost none, or is predicting a lot of them, and we're seeing almost none. Right, so this is telling us we need to go in and fix this, fix this network. That's another example. Now it turns out once you have this model set up, you can estimate it all over the place. And this is a nice little paper. It's a great exemplar paper for how to do these models by Stephen Goodrow, Martina Morris, and James Kitts. Applying these models to the Ad Health Network, so all 120 some odd schools that they used in this case. And it's also a nice way for us to see the kinds of models they put in. And so what they did are they had different kinds of row effects. So these are actor effects. And so we have do 8th graders, 9th graders, 10th graders, 11th graders, 12th graders. Are they differentially involved in their networks? And so what you see is that 10th and 11th graders tend to have more ties in the network than do seniors, 8th graders, or 9th graders. And so when you're embedded in those middle grades, you're sending out more ties to other people in the network than if you're not. Blacks tend to send out slightly fewer ties than whites, Hispanics slightly more than whites, Asians slightly more than whites, others about the same. Men and women don't differ that much in how much relational activity they have overall. Please, go ahead.
Does the confidence interval shrink with the size of that? What drives the confidence intervals in that previous one?
Yeah, it tends to be it's not strongly related to the size of the network, because remember each network is a single observation, right? And so the fact that I have a really big network is only going to lower my confidence intervals if it's the case that I have a really strong pattern relative to what the volume of a random graph would go on. So it really is, there's some convergence that happens on large graphs because the random graph sort of features take over. But by and large, the driving feature in any given model is not the size of the network, it's the randomness of the network, or the comparison of the randomness. So what you're seeing here is a collection of coefficients, right? And so the fact that we have 120 schools, one school has really high observed Hispanic out degree, another has really low out degree. And so what we'd like to do is imagine, like, is this just random error, right? Is it just that some schools are higher than others? Or is there something systematic about this school that makes the Hispanics more egregious, or, what's the word? Gregarious, thank you. Egregious is entirely the wrong word. Gregarious than those that are non-Hispanic, say, right? And this is what I love about having this kind of data, is that if you have multiple networks, you can ask how much natural variability is there in the parameter, given that I have a sample of networks. We don't usually have that, but in this case we do. And so then you can put it in a multi-level model and say, can I predict that variance, or is it random? And sometimes it is, and sometimes it isn't. Then across these different schools, so these are node level features that are just saying like how much sociality, how involved am I in the network. These are node matching or mixing parameters. So our 7th graders are more likely to be friends with other 7th graders than they are with anyone else. And this is our 7th graders more likely to have more out ties than anyone else, right? And so there's some variability difference across grade in their involvement in the network. There's a lot of variability, differences across grade in the extent to which they're friends with each other, right? So junior high kids are almost entirely self-contained. Again, the middle ranges tend to have more cross group ties than not, but everyone has more in-grade ties than they don't otherwise, which makes a lot of sense, right? These are the people you're exposed to. So simple propinquity probably accounts for a lot of this grade mixing effect. Race mixing and gender mixing, right? So boys and girls are more like I don't know what we call adolescents. Adolescent males and adolescent females are more likely to be friends with each other than they are to have cross-race friends or cross-gender friends, even though our design in ad health asked for cross-gender ties. And then this is this triad parameter. It says that it tends to be the case that in all of our schools that friends of a friend of a friend does in fact seem to hold. It is the case we find more closed triads than we'd expect by chance across all of these settings, given this marginal return sort of specification of the model. So I just wanted to sort of point out this is how you can interpret these models. This is a very nice, clear way to do it. We have a paper, David Deal, Dan McFarland, and myself, Jeff Smith, looking at the same data set, but trying to assess the roles in which hierarchy plays in the network. And so we take the same set of terms, but we've added a term based on the Triad Census that allows us to figure out whether or not the network has a hierarchical structure or not. Right, so is there an ordered ranked cluster structure in the network or not? And we find out that in most of our schools, right, both in the cross section and over time, that we tend to find a fairly strong tendency towards hierarchies, but that hierarchy has that tendency has a lot of variability across schools. And so what's fun about this paper is that we're able to go in and explain what some of that hierarchy is due to. And so it turns out that the Lord of the Flies is correct amongst adolescents, right? That if you give them no structure, they create a rigid hierarchy and beat the shit out of each other, essentially. And so the kinds of settings where the world works well and people are nice and sort of engaging are really pretty engineered settings, right? You have tracking, you make sure that kids are engaged, there's lots of cross activities, right? You don't just let them go wild, because left to their own devices, people are not nice. At least adolescent boys are not nice. But because we have that simulate feature in the model, right, we can then back predict. We can do these we can ask ourselves some questions about how different school features might, the slight changes in these parameters affect the observed setting. And so what we're able to do is take the observed space of parameters that we've observed in our network in terms of the amount of hierarchy and the amount of clustering in the network, and we can say, let's draw an example from this set, block model it, and see what that network kind of looks like. And so in this region of the space, you get this very sort of low hierarchy, very hot, lots of really tight clustering. This is essentially a world where people are living in different spheres. This hierarchy is hardly there. Whereas over here in this part of the set, there's a leading crowd that is very highly tied to each other, and everyone else is really oriented around that leading crowd. And so with these two parameters, we can generate very different kinds of schools that are, or our model suggests that there are very different kinds of schools that are coming out of the parameter space of this set population. And so this is just an example of the kind of thing you can do by back predicting from that simulate function, which is a power we never had before. All right, so that's the thing that's great about the great thing about ergo models, and the reason I love them, I think they're fantastic, I have a little poster of them in my bedroom, right, is that, not exactly, but not entirely untrue, but is that you can really, if you think carefully about the way your models are set up, right, and you have a clear theoretical notion about how social structure unfolds, you can operationalize that structure as a parameter in the model and test it. The thing I hate about ergums, right, that drives me nuts, is that you have to have a social theory to specify a structure that actually works, right? And we might not have that, right? So if you know a setting, the good news is because of the last 50 years of convenience samples and networks on high schools, we know a lot about how high schools work. And so we can specify these models pretty well. We have an intuition about them. We have a lot of ways, and we've all been through high schools, right? So we have a sense in which we can do these models and make sense of it, right? I have very little intuition about how terrorist networks work. I have very little intuition about how transgender men's networks work, right? And so in order to think about those settings, and I want to understand them from a health standpoint, these models are really difficult to fit, and you're really likely to misspecify your model. So wouldn't it be great if we had a model that does all of this work but doesn't require all of this sort of theoretical machinery and is nonetheless robust to that? And the answer to that are known as latent space models. So what latent space models allow you to do is they're specified in the exact same kind of way. We have some probability of observing, the notation is a little different, but the idea is the same. We have the probability of observing a tie between I and j as a function of some features that we've observed in the network and the position of I on some dimension and the position of j on some dimension, or their difference in that position, right? And it turns out that these z's now are not these observed statistics that we're calculating, but instead are a latent dimension. And the theory and the model is set up that we just pick these, right? We make them up out of whole cloth. We invent these. That's what a latent factor is, right? This is something we've invented. We don't invent it at random. We invent it such that people who are close in the z space are likely to be tied to each other. People that are far in the z space are unlikely to be tied to each other. But we don't have any idea what z means. We might ex post or ad hoc be able to figure out what it means, but all it's doing is soaking up that variance. And what's beautiful about that is that it works really well, right, to be able to figure out, so here I have z1, I have z2, I can predict each person's position in that latent space, and I can then fit the model to that, and we can see that there's a tie likely if you're close in that space, unlikely if you're far in that space. This is very similar to the spring embedder model we talked about. It's in fact not entirely unrelated. And we can do posterior draws from it. We can say that in fact this person here's position is pretty uncertain. We have no idea where this guy is. He's kind of all over the spot, whereas this person's position is very well known, right? So for a small network that works well. But the real advantage of these models is that they don't require me to specify a particular functional form on transitivity, or that I have a 2k star preference versus a 5k star preference, or that reciprocity is within sex as opposed to between sex, right? So I can be ignorant about the social process and still fit the network. Now, you might do then if all I know is this, I might sit here and squint and say, well, it turns out that I have some attributes on it, that this dimension is education, and this dimension is part of the city you live in or something. And so there's often, as an exploratory tool, a good way to think about the dimensions that matter. I can then go add those back into the model as observables and see if there's any structure left over beyond the observables, right? So you can do this iterative model fit where I use the dimensions to help inform what I put in the model to learn about the space, and then from that space find something else. Or you can just use it as a way to control for variance you don't know about. All right, so you can turn out these models are really easy to fit, just like before. Instead of the ERGM, it's ERMM, so it's the I don't know why there are two M's, but you just fit the model through that set. You say it's a latent with 2 dimensions, right? And you, I'm going to get the fit here using a maximum likelihood estimate. Turns out you can do lots of other things to the model, right? So I can say that the dimension isn't just Euclidean. It's not just that we have equal difference in the space, but there might also be some extra variance that's soaked up by clustering in the network. And so I'm going to assume that there are 3 groups in this network. And I'm going to say, in addition to the overall space, you get an extra boost if you're also in the same group. And so the model simultaneously fits the number of the group structure of the network. So it tries to, so now we're making up a number of things, right? So we're making up a position on Z, a position on Z2, and a membership in a group. And we optimize those all simultaneously to find out the best fit for the model, right? And you can do Ds, you can do 2-dimensional fits, you can do 3-dimensional fits, you can knock yourself out. Don't go crazy, right? It's hard to make sense of, but there you have it. This is an example of one of these on the Prosper data. Again, the nice thing about these models are that they don't require you to understand what's there, but they are also a great way, especially in the health field, if what I really want to know is whether or not my intervention had an effect on changing the tie structure of the network, right? And I know that my intervention was ineffective, that there are lots of different ways that people sort of took up the treatment or not, for example. I can fit a latent space model and then add my treatment condition to it. And if there's other selection features in the network that drive the structure that I'm unaware of, right, I've sort of given the boat to them. I've said, here you have it, knock yourself out. Is there anything above and beyond that I can get out from my model? And that's a really tough test, right? So I've essentially given all the extra variance to this latent space. But even if I know that, is there enough signal from my treatment to find an effect that would pop out in this kind of set? So it's a really nice way to do it. The downside of these models is, as you might imagine, like you're having to do a lot of things under the hood. So I have to optimize on 2 or 3 dimensions. I have to assign people to groups and these kind of things. These models take a long time to fit, right? So just be a little bit patient, and you got to let the model run. Go out, have a cup of coffee, come back, and it'll be fine. If you're doing this on a model of 1,000 nodes or something like that, set it up on your cluster, go home, right? Have a nice spring break, come back, and it'll be where you want it. If your goal is sort of out-of-alpha prediction only, so if you're just trying to predict the future, or you're ignorant about the setting, or your goal is just to control the noise, then a latent space model is probably exactly what you want. If you understand the setting well enough to specify the conditions that drive a network parametrically, like what are the structural features that are doing it, then an ergom model works better. Ergoms fit faster. They're still not super fast, right? But they fit faster than latent space models. They can do slightly larger networks, and so they're nice in that sense. Now it turns out that there's one last sort of development recently. This paper came out just 2 years ago by Hoff and Wolfowski on the additive. It's called the Additive and Multiplicative Effects Models, or the AMEN package. It's one of the best best acronyms I've seen in a while. But you take this basic notion of conditional independence, so that is that the I and J, if you're willing to assume that I and J are independent once I've controlled for the network features, and once you have the latent space, you can do that. Right? If that's where you're at, then you can say, all right, once I have this set up, I can estimate these using pretty standard MLE and MCMC chain sort of effects. And so it's not that hard to get reasonable estimates of these error structures if I'm willing to assume the latent space is being sucked up by a lot of your dimension on A and your dimension on B, net of everything else I do. What they do is they then add a series of features that are thought of as these latent multiplicative covariance features that allow you to capture things like transitivity in the model and other types of features that are much more general than the kind of erg effect, but nonetheless capture some of the same kinds of ideas. So you can get reciprocity, you can get transitivity, you can get sort of local cycles as features of these interaction effects, essentially between features of U and features of J. And so they're really, really flexible models. Moreover, because Hoff and Wolfowski are both really good pragmatic, practical analysts, there's a lot of really nice features in this package. The package includes a way to fit missing data on the fly, right? So if you have some ties in your network where you don't know if it's a 0 or a 1, this is something people always forget. When you put together a adjacency matrix and you think you've collected all your 1s, right, you've actually also collected all your 0s, right? So all your 0s are 0 with certainty, right? And so if you don't know that that's true, then you really want to make sure that you, if I don't know that this person didn't nominate that person, then I want to treat that as a missing dyad as opposed to a 0 dyad. And this model framework allows you to do that really quite simply. It also allows you to fit any structural type of dependent variable, right? So it can be a quantitative dependent variable. It can be that my edges are valued as opposed to binary. It can be all kinds of different, it can be an ordinal variable. They have different kinds of models built in for the design of the survey. So they have this fixed rank nominations model, which says that given that I've limited my network to having a degree of 5, I can only nominate 5 people, and the first person is a better friend than the second friend, right? That's information that our survey has. Let's build that into the model. So all of these things are able to build into the model. I'm not going to go through an example of it because if you think latent-based models are slow, these are even slower. That's the one problem with them. They do take a long time to run, but they're very flexible. Alex Wolfowski gave a great presentation on these models last year. There's a video of it up on the website. I encourage you to go look at it. If your networks are of reasonable size, like less than a couple hundred, these are worth taking a look at. If you're a hardcore statistician and want to develop these models even more for very large networks, we would all be very, very thankful. So that's why I'm putting that out there. And that's what I got. So this is everything about statistical modeling of networks except the part that you care about most, which is causal inference and on dynamic networks, which is coming tomorrow. But that you need this foundation to get there. All right? Questions, comments before we break for coffee? Please.
So thank you so much for the presentation. I'm just curious about all of these statistical packages now. So I have a background in data and now learned R, and now we talked about UCInet. So I'm just curious, in the lab, are we going to touch on how to kind of move data sets between these different platforms?
Yeah. We hadn't planned to. It's a good idea. Maybe we can get, maybe the grant can pay to put up some tutorials for doing that. That'd be a good idea. It's kind of the world we live in, and it would be great if at some point somebody would, sort of pull all these things together. And I think that 10 years from now, that's probably where R is going to be. That all of you are going to get sick and tired of moving to UCInet to do the QAP model. And so you're going to take Carter's version of QAP model, update it so it works right on R, and it'll run. But in the meantime, in the current time, we really are stuck with usually to move between packages, converting to either tab delimited or CSV files and moving it back and forth. And so, in terms of there are some packages that you can move in and out of nicely. So R reads PAYEC files and writes PAYEC files, for example. It writes the kind of files that UCInet can read, but it doesn't read native UCInet files. And so moving in and out of it isn't as difficult as it used to be. You don't literally have to create a new raw text file and read it in, but it's still pretty cumbersome. So, and that's unfortunately the state we're at. I think that if I were giving advice to people who are just getting started, I guess is what I'm doing, I said, if you have a single network, right, so if you're not in like an ad health or a Prosper situation where you're trying to compare hundreds of networks, but you have a single network, even a dynamic network, and you really care about it, these are kind of association tests, like QAP kind of tests, then investing in learning UCInet is worth the effort. And because it's not a complicated program. It's a relatively straightforward program. It has a nice GUI. It keeps a log, right, so it's the kind of GUI that I like. It's not something you can do something and forget what you did, so you can go back and pull up the log. Under the hood, there's a scripting language, so you can write programs for it if you really want to. And so it has all of those features built into it, so it's a very nice program in that set. The main limitation of UCInet is that it doesn't deal with multiple networks easily. So if what I have are 100 ad health networks, I have to either write a script for running over my same analysis over and over again 100 times and storing the output, or I got to go through and pay a bunch of RAs to do the analysis 100 times, and that's just untenable. And so I think that problem is there are ways around it when networks are small. You can stack what are known as multiplex networks, so you can stack networks in UCINet and run them separately, but it's hard to do. But if you have a single network and you're interested, especially in descriptive features of the network, so the UCINet still has the best suite of all the centrality scores you could want and the K-core kind of scores. They're all in there, and that's really a nice feature, especially if you have something particular you want to get. But it's not a programming language, so it's hard to do anything other than what's baked into the menu. That's the main thing. Please.
Are the ergos and the latent variable models, are they specific for directed network?
No, that's a good question. So the question is, are these models specific for directed or undirected or types of networks? The answer is no. They fit for directed or undirected, binary. You can do ordinal with an ergom now, sort of model, so low, middle, high. Don't go crazy and have like a 16 value ordinal set. It'll take forever to fit, and there's not enough data support usually. But if you can break it up into something like low, middle, and high, they usually work pretty well. You can also do temporal models, right? So you can do them either in panels, if I have, it's a time 1, time 2, or if I have an actual time dependence. I have these things called tergums, which are temporal ergom models, which allow you to fit a separate model for the formation of ties versus the dissolution of ties, right? So it's a very nice, flexible two-model framework. And you can also fit bipartite networks. And all of these packages, including, all right, I'm going to hold my tongue on latent. I'm not certain that latent net will do bipartite networks, but amen will, and as will ergom. David, do you know if latent net will do bipartite? Okay. But so it's 5 years ago the answer would be no, all binary, directed, you're sunk. But that's not true anymore. It really has gotten quite flexible, and I really got to give props to the StatNet team out at Washington, the Tom Schneider's at Utrecht, and Peter Hoff, here at Duke, have all been working on these models really hard for the last 15 years, and they've gotten to the point now where the community can use them. And so this is volunteer work on their part, and they've done a great service to the community. So, any questions? All right, I'm going to take a break, grab some more coffee, wake up, and then you get to hear me again for another couple hours talking about diffusion. So.